Ivey.
Oh, so
Was a final-year student at CalTech, working with Owens. They have been working on leading space weather characterization efforts, studying looking for radio observations, and as well as optical monitoring of stars. You guys hear about that? Yeah.
Everybody for coming. As a disclaimer, because I have been working on the instrumentation for studying solar space, I'm going to be a very instrumentation focused talk. We also talk a little bit about my athlete. To start a little bit about what I mean when I say space weather, or perhaps more generally space climate and weather. This is referring to both the radiation as well as the particle flux from a star. So on the quiescent or perhaps the climate side of things, that would include the atmospheric flux, just coming from the surface of the star usually, as well on the particle side, the solar or stellar flux. On the transient side, though, or the more weather focused side, that would refer to flares as well as coronal mass ejections, or solar, or presumably also stellar energetic particle events, or CMEs and SEPs. And this transient component is what I'm really interested in. What I'm really interested in is being able to explain coronal mass ejections on these stars. So the way I'm doing this is in part by referring to the optical continuum of these stars. This is specific to the white light component of these stars, which is just the chromospheric heating that produces a black body emission. And this is pretty important for understanding flares in space weather, because the bulk of the flare energy is expected to be within the white light component. And even more importantly, there's rough partition that's expected between flare energy and coronal mass ejection energy. So understanding the flare energy can give you some good rough estimates on the limitations of the CME energy. And the way this looks like on other stars, it's like this, sort of a canonical flare profile that we see at least with the sun, usually in the X-ray, but this is a certified test at a relatively red wavelength. The significance of these sorts of flares is that from other stars we see hundreds to thousands of times stronger flares than we see from the sun. So we should expect fairly strong events over terms of the radiation as well as the particle flux. And then on the other side, the price spectrum I'm using is low frequency radio, below about 100 megahertz. For those who like wavelengths, that's between about 3 and 20 meters. So this is going to be sensitive to the plasma emission that's caused by particles moving through the corona of the star. So that way, they're really good for actually tracing particle flux and the state. Just to give a little bit more background on the radio side, because it's a little more complicated and we'll tend to be a little less familiar with it. Just starting with our canonical flare model, where you have magnetic reconnection indicated by those that gray bar with the arrows by it. At that point, you get acceleration, bright, and extremely energetic flares. You can snap within the wavelengths that were responsible for containing that plasmoid. And in that case, that's when you get a coronal mass ejection. That's when the plasmoid is capable of escaping through those field lines. But also in the process of snapping those field lines, you're getting particle acceleration along with them explicitly. That's when your flare associated SEPs. And as it turns out, as your CME and your SEPs are traveling through the corona is in fact the plasma, and so these particles are going to be exciting plasma emission, with lower density plasma being higher in the atmosphere. And as it turns out, density or the frequency of the emission that you see from the plasma is practically related to the density. So what you end up seeing then as the coronal mass ejection or the SEPs travel further into the stellar or solar atmosphere is that it's exciting lower and lower frequency emission. So you get characteristic sweeping structures that look a little bit like this. So this is a dynamic spectrum produced by the OVRO-LWA, which we'll talk a little bit more about later. But all this is intensity as a function of frequency as well as time. And there are a couple structures I want to highlight here, namely this vertical striking structure right here, which are the three bursts. These are associated with those SEP events that are accelerated to about half the speed of light on those field lines. That's why they are so vertical in nature. They are sweeping to lower frequencies much faster than, say, the coronal mass ejection, which is producing this slower drifting structure in the dynamic spectrum. This is what's called a two burst. And because it is driven by or produced by the shock, driven by the CME, is moving and drifting at the rate of the CME's velocity. So type 2 and 3 bursts are exciting because they are direct of the coronal density profile, which is notoriously difficult to measure for other stars. So being able to make a stellar detection of this sort of emission is great for sort of constraining the plasma environment of these stars. They're also great because they are directly related to particle flux enhancement through interplanetary space and at Earth specifically. So they're great for actually constraining whether or not there's particles escaping from the sun. Unfortunately, or maybe fortunately for the sake of my thesis, there's no stellar equivalents that have been published as of yet. And there's a few reasons for that. For starters, there are quite stringent sensitivity requirements. The brightest solar type 3 bursts are on the order of 10 to the 11 Janskis at these frequencies, which at 10 parsecs puts it at 4 millijanskis, which for folks that aren't as entrenched in radio, or is sort of the premier radio instrument working at these frequencies that would be low for. The sensitivity is on the order of 100 millijanskis at 1 second. So you need quite high sensitivity in order to detect them at the sort of distances that stars exist at. The other issue is that the time resolution required to detect specifically type 3 bursts is quite high. Those type 3 bursts, which I'm showing here on the right, this is just a zoom in of that we're constructing that on the previous slide. They only last about 10 seconds. They sweep through the band within about 10 seconds. So in order to actually resolve the structure of the type 3 burst, to make sure you're on track to be maybe the 3 burst patterns and another transient event requires a high time resolution in addition to that high sensitivity. And then finally, the sort of stars that have been targeted historically for radio emission have been imports with exceptionally strong magnetic fields. When you have a strong magnetic field, it's hard to drive a shock, at least to superampanic velocities, which means that you're probably not going to see a type 2 signature from an import. The other problem is that those magnetic fields can also inhibit the actual emission escaping from the star. So if you want to detect a type 2 or 3 burst, especially if you want to snap those field lines, you need to look at a star with only maybe moderate field strength, not the kilographs fields that emitters have. So what this sort of boils down to is that in order to detect these bursts, you want to look at nearby stars, as well as stars with only at most moderate field strengths. And so that informed the stars that I'm looking for the space weather around the Sun's program, or you'll hear me calling it SWAYs. So I'm looking at nearby stars, and stars within about 15 parsecs, with the exception of the UK draw at 34 parsecs. There's a paper just this week about the magnetic topology of the star. It's a really great candidate for CMEs, so it's the exception here. All these stars, though, are really young, so generally pretty active, and they're all solar type. Heavy quotations, everybody has their own definition of solar type, it seems, but for me, that means they're going to be about 5,000 to 6,000 Kelvin and not evolved. These are main sequence stars. And the SWAYS program specifically, what makes it fun and unique is that it is a monitoring program. So we're going to be staring at these 5 stars, just these 5 stars, for as much as possible. And that's going to be happening simultaneously beyond the phone as well as the radio. So in order to do that, these are the instruments that I have been working on, namely Flarescope and the optical, looking for the Ivey syndrome. The data product coming out of that instrument is going to be a light group. It's a photometric instrument, but the sort of neat thing about Flarescope is that it reaches sub-millimeter precision on few-minute timescales. And then on the radio side, with the Owens value on wavelength rate, or the OVRO-LWA, that is operating below 100 megahertz, so it's going to be responsible for looking for those type 2 and 3 bursts. The there are two data products that are going to be relevant for the science that are coming out of this instrument. Namely, it's going to be producing low time resolution pictures as well as high time resolution spectra. So I'll talk a little more about that in just a minute. But again, just want to emphasize that these instruments are observing the same stars simultaneously all night, every night, weather and electronics permitting. So to start with the radio, so I can use opticals at palette cleanser at the LWA is composed of 352 dipoles, which is a little bit different from some other radio instruments you may know of, like the Observatory or the VLA. These dipoles do not point, you cannot mechanically move them, except the cows that rub up against them. Each antenna is going to be sensitive to the entire sky, and then you can either sum the signals and weight them such that they're sensitive to a specific direction, like is indicated here with beamforming, or you can cross-correlate the signals in order to create all sky images like this. And with the maximum baseline of the OVRO-LWA at 2 kilometers, at the frequencies it's operating at is the spatial resolution of about 5 arc minutes, which is not impressive maybe to optical astronomers, but is quite nice for radio astronomers at these frequencies. The frequency specifically being 13 to 88 megahertz for 24 kilohertz resolution. That high spectral resolution is going to be important for actually being able to resolve this radio structure. And at the 10-second integration time, that is going to be about 100 millijan speed sensitivity, which, if you remember, the type 3 burst, that 10 parsec is requiring 24 millijan speed sensitivity, so we're not to that extent, but for epsilon irradiating, which is something sort of interest at 3.2 parsecs, that would be the equivalent. A 5 sigma detection at that sensitivity would be the equivalent of a 10 to the 11 gene speed burst, so right at the solar threshold for these kinds of bursts. And again, these are simultaneous observing modes, so the slow visibilities or that cross-correlated data that produces images like this. And then there's also the beamforming mode that produces the dynamic spectra that I showed earlier with the type 2 and 3 burst. And the nice thing about beamforming is that it has really high time resolution. So again, it's going to be good for actually resolving the structure of the bursts. So a little bit about how we're using these two different data products in order to do this search. The first thing about the slow visibilities is that because it is cross-correlated data, we preserve information about how the signals arrive to the individual antennas. That allows you some fine control over the shape of the point spread function. So that's really nice for resolving structure and also sort of removing the sky from the science that you're doing, so you can really hone in on just the star that you're interested in. The fact that you're producing images also makes it a lot easier to identify radio frequency interference for RFI, as well as flag it. The problem though is that these visibilities, this cross-correlated data is on a 10-second time resolution, so it alone cannot resolve the burst of type, resolve the type 3 burst time. Beamform data, on the other hand, it does have the high time resolution that we're interested in. Unfortunately, it doesn't have very good beam structure because it is a sum of signals rather than containing the information of the individual antennas. So the beam size ends up being closer to a degree rather than 5 arc minutes, which isn't ideal. And because you do lose that spatial information, that makes you a lot more susceptible to RFI. It makes it a lot more difficult to flag. As shown here, lots of RFI, which I'll talk a little more about later. But this sort of boils down to that we should probably be using these slow visibilities that are actually sensitive to identify burst candidates, and then use that to inform where to look in the beamform data in order to actually characterize the burst. So the data that I'm going to show is going to be based on a 1-hour observation of the star Pyroclima. This is a relatively young star, 10 million years old, really fast rotator, about 5,700 Kelvin. That temperature actually makes it one of the hottest stars of the sample, which, as I'll talk a little bit about later, actually makes it kind of difficult to detect flares from in the optical. It's also 14 parsecs away, which makes it one of the furthest stars in the sample, which is going to make it difficult to detect radio emission from. And at a magnitude of 5.9 actually makes one of the dimmest stars in the sample as well. All of this to say that Ivey was probably the most difficult star to do this science with, so we should be able to expect to do science with it, we should be able to do it with the other stars in the sample. That said, are we doing that to start with the visibility data? So in principle, what I would be doing is using the visibilities to measure the flux at the location of the star, look for an increase in the flux, that's first. In practice, the ionosphere has other plans for where that star is in the sky. What I'm showing here is just a frame centered on pan-chromatic indicated by that red star, and you can see that these sources in the sky that are persistent like to wiggle around a lot because of the ionosphere, similar to the way that the atmosphere impacts both the flux and the resolution in optical data. And as it turns out, what I'm showing here on the right is the separation of the sources from their average source of the sky. Not only is it a bit periodic, but it's periodic to different degrees and at different times. So the ionosphere is affecting different sources at different locations in different ways. That makes it a little bit tricky to actually guess where your star is going to be in the sky. Thankfully, I guess Ivey was right by a really bright target, so we can kind of estimate the Ivey's position is changing the same way that that source is. But yeah, unfortunately, the effects of simulation is as changing the source position, similar to the optical exchange between intensity as well as the beam or the PS shaded size. And all of that makes calculating the flux really difficult. Our sort of way around this is to start with our image centered on Ivey, then mask it out. So covering up in the visibility space and then really deeply cleaning, cleaning everything that does not include Ivey so that you can get a nice image like this, just a residual. And then the results of extracting flux from that looks like this. Where the black is the flux that was pulled from the position of Ivey, and the images like the one on the top, and the red is the flux pulled from images at the position of Ivey from images at the bottom. And not only is the flux more stable over time, because the effects of the simulation was having on the bright sources removed, but the RMS in general is lower. Unfortunately, the RMS is not to the noise that is theoretical for the OVRO-LWA. It's about 740 millijanspeeds, which is decidedly not 100 millijanspeeds. So a 5 sigma detection from Ivey at 14 parsecs would be about 10 to 13 janspeeds. So a couple orders of magnitude higher than the brightest solar type creepers. But if stars are good at anything, they are good at producing things that are brighter than we see from the sun. So it's hard to say whether we should be able to expect a burst like this from these stars, but following trends the importance of this spectrum, I feel pretty confident. Yeah.
You mentioned this was a younger star.
It's a pretty young star, at least by my standards.
So there's certainly a chance that it might produce more of a how do you know how young it is?
200 million years old.
200 million.
Yes. Yeah.
So real toddler.
Yeah, it has time. Yeah, and super flares have been detected from Ivey. It's known to produce really strong emission at other parts of the spectrum. So yeah, I'm not ruling out into the 13 janspeeds from it. So there was no burst in that data. But in the instance that we do detect a burst in visibility data, then we would go to the beamform data to try to characterize the structure. So in principle, we have 256 millisecond time resolution. And what I'm showing here is 256 millisecond time resolution dynamic spectra with model type creepers of various drift rates. Once we integrate down, we end up getting some profiles that look like this, or light curves that look like this. Or these solid lines are the light curves as they exist for the bursts like this, but in principle, you could de-disperse this wave of the first, similar to how people do searches for pulsars. And the parameters that give you the highest signal, which is indicated by the dashed lines, then that would be the parameters associated with the type of first, and in that way, you can start to constrain some of the beam as well as coronal properties for the star without being able to natively detect it in the dynamic spectrum. That's how it would work in principle, but in practice, this is what our dynamic spectra look like, which is to say bad. At low frequencies, you're getting really close to the ionospheric cutoff. So 10 megahertz, the sky is essentially opaque. And when that happens, it's really hard to get flux calibration. So below about 27 megahertz, you get really poor calibration. That signal right there is an hourly signal from the Los Angeles Department of Water and Power, checking the moisture content of the soil. This is only an hour-long observation, so you can't see that it does in fact show up in the next hour, and then after that, thankfully that makes it predictable, but still not ideal. And then finally, these striking structures is digital television, and actually the sort of sporadic structure just below 70 megahertz is reflected digital television. So there is a lot of RFI and beam-formed data that is a consequence of the fact that it is the sum signal of the antennas, so we can't, in pre-processing, remove the RFI. So what this sort of boils down to is that beamforming as it exists right now is not going to be super useful for this science, unfortunately. But working with other folks on the OVRO-LWA to make some remedies that are non-trivial, which is why they're not currently implemented, but hopefully it'll be useful for science in the future, or this science in the future. It's great for solar science. So just to summarize what we're seeing in the radio, the visibility reduction needs more because it does need quite a bit of processing that involves both understanding how the sources move in the sky and then cleaning after you know how the sources move in the sky. The noise level as a result of that isn't ideal, but is probably still conducive to being able to detect this kind of emission. Beamform data as it operates is not going to be useful, but I've been talking strictly about type 3 bursts, but those type 2 bursts last for tens of minutes. We could in principle integrate down the visibility space to get the sensitivity we would need to detect them. And at that point, we could also use visibilities at 10-second time resolution to constrain their structure and what that means for the coronal properties of the star. And also, the type 2s are what are related to CMEs, so that's arguably more interesting anyway. So that was radio. Now to optical. So in the optical, again, I'm looking for the white component of this sort of activity. And stellar astronomers like to model flares of 9,000 Kelvin black body, but I think if you talk to any stellar astronomer, they'll also say that that's not right. But what this means is that these flares are going to peak at lower wavelengths than your stellar photosphere, and it also means that because it's a 9,000 Kelvin black body superimposed on a 6,000-ish Kelvin photosphere, your volumetric contrast is going to be quite low, which is why historically detecting flares on solar type stars in general has been quite difficult. Also, because we need to look at nearby stars to accompany the LWA, and because these are solar type stars, these are going to be really bright stars. As I mentioned, Ivey is one of our dimmest stars, and it's still 6 and 7 back. So at that point, you run the risk of saturating the detector. And these are the sort of restrictions that, oh, yeah, Dave.
You said that if you ask a stellar astronomer whether a 9,000 K black body is correct, they will say no. I can think of a lot of different ways that that would be a bad assumption. What are some of the ways that make it especially bad?
That make it especially bad?
Yeah, like I assume it's not a black body, and I assume 9,000 K is bad.
Yeah.
So like both words are bad.
Yeah, so the 9,000K, I think, primarily comes from solar observations, where that might be accurate for like photosphere and white light kernel, there's very different uses for that. But some of these stellar flares, even if they are black body there have been results that show that you can see emission from the loop itself. So treating it as like the foot point emission is not going to be accurate. There's going to be a variety of factors along the way that are impacting it. Yeah, and there have been recent results in the UV, maybe the near UV, that show that these temperatures can actually be upwards of like 20,000 Kelvin. So a lot of flare energies have likely been underestimated by assuming a 9,000 Kelvin black body. Plus, I mean, the decay of the white light flare is a cooling off, so the spectrum is evolving over time.
That's good for me. Thanks about planets to know. Sorry for messing up your flow.
No, this is great. Yeah. So yeah, if you want to detect a flare by lightning type precision, and I'm specifically interested in accommodating bright stars. So for that sake, I designed a Flarescope shown here, and its little dome on that Hellenmark. This is a 0.5 meter aperture from PlaneWave. I would highly recommend PlaneWave. They're a great company, great to work with. Also make great telescopes, it turns out. And in order to accommodate those bright targets, I am using diffusers. Namely top hat diffusers from RBC Photonics. I have a 1/4 degree, 1 degree, and 2 degree diffuser available, but they're stacked in a little filter wheel with 5 spaces on each carousel. So also have the option of no diffuser for those indoors that, you know, at some point show up in the science spaces. But this is going to prevent saturation on the detector. Namely, the optical path is designed such that the brightest star, epsilon Arcturian, does not saturate the detector with the 1 degree diffuser. The primary science band is the slim G band, about 405 nanometers. This is going to give better contrast for those flares in the R, I, and Z filters that are upwards of 800, 900 nanometers. And it's also not going to be affected as much by the atmosphere as the U band. Also, U band is also heavily affected by the quantum efficiency of our detector. Our detector is going to be operating, or does operate at 1 megahertz readout, which for a megapixel chip, that's about 1 frame per second. And we need to read out pretty slowly to mitigate the effects of read noise. Because I am using diffusers and in fact using over 1700 pixels, the noise contribution per pixel really adds up. The nice thing though is that I do have simultaneous read and exposing capabilities because it is a transfer CCD. So even though I'm sort of limited by the readout for the exposure time, I can still have a pretty high imaging cadence. And then finally, this is all mounted on a drive mount, which and it's also on an equatorial edge, which that's going to reduce the noise due to interpixel variability by mitigating the tracking issues. So what that boils down to is producing precision on the order of a millimag over 5 minute timescales. But what I'm showing in this figure is just the different noise contributions, and I just want to point out that scintillation noise, this blue line right here, that is the dominant factor for our noise, and it's going to be the dominant factor for essentially any ground-based observatory looking at bright targets. But 5 minute timescales, if we get around it, we get down to the millimag precision we need to detect these flares. So in principle, how we actually end up extracting the data that we need from Flarescope is that calibrate your images, and then make adjustments to the images based on the tracking problems, because tracking really isn't perfect, but make adjustments based on how the position of these sources changes, and then stack your images so that you're not stacking the flux from the star, the background, and then extract the flux from the star using aperture photometry. Thankfully, because I am using diffusers, I have a pretty good idea of what my PSF actually looks like. And in practice, it does actually work exactly that way. Optical has that benefit over radio. It operates as it ought to. So what I'm showing in the top is just the tracking errors over time. So over the course of an hour, it goes maybe 10, 12 pixels. But that ends up producing a light curve that looks like that on the bottom. The black dots referring to the native integration time of the second for exposure time. of 3 seconds, and then the purple dots showing integrating up to 60 seconds. So at the 3-second exposure time, it's already reaching about 3 millimag precision. And after integrating up to a minute, it reaches 7 millimag, and at 5 minutes, it's at 0.4 millimag. So Flarescope's doing better than it was intended to do. But again, the dominant noise factor for these observations is simulation noise. So I sort of suspect that there were weirdly good conditions for this observation, which I'm not complaining about. For that noise that we're achieving after 5-minute timescales, a 5-sigma detection from OVRO-LWA would be the equivalent of about 18 to 32 flare. So that's just a big solar flare. So Flarescope could likely observe the equivalent of a solar flare on OVRO-LWA, which again is pretty impressive because OVRO-LWA is the brightest star of our sample, or not the brightest, one of the hottest stars in our sample. So, just as a summary of how SWAYS has been operating, we know, or we should hope, that the OVRO-LWA should be able to detect extreme stellar radio bursts, but Flarescope is going to be able to detect stellar flares for sure. And I put a little asterisk on should be able to because it has already detected stellar flares. That's a flare from the star in the job. Again, the furthest star in our sample that I made an exception for because it is a quite strong candidate for reducing CMEs. So Flarescope can in fact detect flares. The other thing I want to emphasize is that coordinating observations is actually possible. All these observations were on the same star at the same time. And not only that, but I can observe a lot of stars at the same time. So this is just the information on these stars I've been looking at that I showed earlier, but I want to emphasize these columns here now, where I've collected between the two instruments about 800 hours, these 5 stars. In particular, I've been really staring at EQ draw, so about 190 hours with Flarescope and 170 with the LWA, and about 76% overlap between observing. So yeah, coordinating multi-wavelength monitoring of stars is possible and necessary if you want to be able to do this science. Moving forward for the future of SWAYS, going to keep staring at these stars. The instruments are built, this is what they're meant for, so this is going to keep staring at those stars. But ultimately, constraining coronal mass ejections in space weather in general is a multi-wavelength effort. There's a lot to be learned about coronal mass ejections in space weather at other wavelengths. That's historically how they've been detected on other stars as other wavelengths. X-rays been powerful through dimming processes. UV's been great for sort of constraining any of the flares pictures. That'd be great for understanding the energetics a bit better. But also through constraining CME velocities, same thing with optical spectroscopy. Submillimeter isn't going to be sensitive to escaping material, but it is sensitive to confined electrons through the form of producing gyrosynchrotron and synchrotron. So that can give some really nice fundamental information about the sort of electrons and other particles that are being accelerated in the corona that are responsible for hitting the atmosphere and reducing the white light that we see. So just building up a fundamental understanding of how these play a part. And the centimeter regime, this is going to be sensitive to non-thermal, incoherent, and coherent acceleration. And actually, I wanted to focus on this for just a few minutes because this is related to science that I've been doing that's not instrumentation. So I just have a couple slides on some cool stars that I've been studying through the VLA and through tests. VLA tests still optical and radio, different wavelengths, different instruments, but some of the same fundamentals. So test is also sensitive to the white light component flares. And I was referring to catalogs from 2 et al. In 2020, also VLA et al. In 2020 that were identifying super flares with solar giant stars from the first year of test data. So these are primarily southern hemisphere stars. Tests are probably, well, no, I don't know. It's a 2-minute cadence, or the data I was using is a 2-minute cadence data from test. Test is nice because it is a monitoring program. So it spends 27 days at a time per star, operating at red wavelengths, so not great for detecting solar flare scale flares on stars, but it's found a lot of super flares. So I'm using stars from those catalogs from Formula to look in the VLA Sky Survey or VLAS. In particular, I was looking at class 1 and 2. The fun thing about VLAS is that its cadence is 5 seconds every 32 months. So the odds of detecting transient radio emission in it are quite low. Despite that, of the 150 stars that I looked for radio emission from, I found 6. And as it turns out, the properties of that radio emission does seem to be consistent with the radio emission being the radio analog of the super flares that we see in the optical. That said, there were 2 stars that I liked the best. The first is the star, really young one, about 40 million years old, based on its association with the Columbia group, and it's making a lot of flares. 40 million years old is producing a lot of flares, about 200 per year. And the neat thing about this, I said I was only searching epochs 1 and 2, but it was actually detected in all 3 VLAS epochs, which is bonkers. Those are 5-second exposures spread out by 32 months. That's not really consistent with this being transient emission, but it's also brighter than to the 11 Janssen burst, which is the brightest burst that we see from the sun at these frequencies. So this would be unprecedented for fluorescent emission, but without simultaneous observations at flare-sensitive wavelengths, we can't really say what it is. The other star is this guy, a bit less than 10 million years old. That said, it's actually producing way less flares than HD 295-290, about 60 super flares per year rather than 200. It was only detected in one of the VLAS epochs, but the emission that we found was 80% circularly polarized, which is without a doubt coherent. And at these frequencies is almost certainly electron cyclotron laser emission, or ECME. And ECME is fun because it directly tells you about the magnetic field strength of the star that's producing it. It's also fun because we don't really see it on other similar type stars other than the sun. We see it from indoors as they're flaring, or from a star like Leo, that's a SETI type variable who's regularly producing it, but those are almost certainly coming from electrons contained within a closed magnetic field loop. But we don't see it from solar type stars. We do see it from Jupiter, added as it is modulated by its moon Io. So that could be a really fun explanation for what's producing this emission. But again, without a simultaneous optical or similar wavelengths, it's hard to say if this is flare related, which is the only time we see the sun producing CME, or if it's some other, perhaps way more exciting emission process. But we need simultaneous observations in order to say that. So all of that low frequency radio is great for sort of doing these particle acceleration studies, especially for detecting CMEs. But if you want to be able to constrain whether or not what you're seeing is a CME, or if you want to know where to look in the radio for it, it's really important to have simultaneous observations. And thankfully, Flarescope and OVRO-LWA are actually performing to an extent where we can do this science. So I'm looking forward to actually digging into those 800 hours of data. Excited by the extractor. And then moving forward to the future, I have an undergraduate that I'm working with who is processing more of the test data to look for superflying stars, to look for more of that VLAS emission, to see if there's any other of these allergic stars that are producing ECME or other from the universe, to really build up the statistics of that front. But it just gave the spiel of was essentially an instrumentation paper that I'm going to be submitting in the next few weeks. And then following that, campaign on the draw, hopefully some follow-up on those funky VLAS stars. But yeah, thank you.
This is all amazing and super exciting. You're asking about your sort of magically working with lots of hard work, magically working optical monitor. it looks, are you getting that photometry without any comparison stars?
Yes.
Which is, it feels amazing to me, yeah.
Yeah, these, unfortunately, one of the side effects of using a diffuser is that it takes a lot of space in the detector.
So this is just like one bright star.
For the most part, yeah, I'm extracting flux from other stars that I can manage to detect in the field, but also when you diffuse, those dimmer stars disappear.
Yeah.
So I'm using them as a baseline if I see something weird in the light group to check if that same weird thing is happening to them, but yeah, there's no photometric calibration really.
Okay, so then that works, is that just, well, like I do a lot of transit stuff where like if we need stability over 5-hour timescales, you need to correct for Earth's atmosphere, but here, because you're looking for short enough bursts, it's okay if like the atmosphere is wobbling around, or is it just always clear, or is that?
Oh, well, so, Flarescope is actually at Palomar,
Oh, okay.
and it is certainly not.
Okay, got it.
But it becomes exceptionally obvious when the weather gets bad, or
Okay.
when a cloud passes over by.
Okay, so yeah, so you just have to, you throw out a lot of that, I got cloud delays. Thanks.
Talking a lot about, OVRO-LWA and the issues associated with getting down to the, like, theoretical noise for the instrument. I'm curious what you think the path forward is for the LWA, for, detecting fainter bursts from some of these products.
Yeah, path forward, first I would probably have it consistently working, because it is, dipoles, that's where the sensitivity comes from, right? And very often, tens of dipoles could be down at a time. That impacts the sensitivity. Also, the cows do actually impact sensitivity, because that affects our understanding of the polarization alignment of the antennas. So having a better framework for keeping the antennas themselves stable is great. Start hardware is not my strong suit. But besides that, we've been trying to figure out a less intensive way to implement peeling, which is structured dependent removal of bright sources. So getting rid of some of the side effects from sources like Cas A that flood the field. So yeah, unfortunately, peeling because it works with visibility space is very time sensitive. So there's some paths forward, but there's not an easy one. Yeah, dude.
Two questions. One is, near the end, you talked about, you know, what's next with this setup, and it was, stare more, keep staring,
Yeah.
and then extend to other wavelength regimes and add that information. I'm wondering if stare at different things is in the realm of possibility, and if that is equal priority, lower priority, and why?
Yeah. So there are definitely some other stars that I'm interested in. Because Swayze is such a small sample, it turns out there is actually a quite solid chunk of the year where it's not being effectively utilized. During that time, I like to stare at an import to make sure, just to double check you can see a flare. So, but there's really other stars of interest to stare, to monitor, to expand to other wavelengths, and that would probably be better than an AG work to confirm that it's possible to do this.
I'll ask my second question. That's okay. Yeah, and this is a naive question, and I should probably know the answer, but it's in the vein of one person's noise is another person's signal, and I'm wondering how much of the noise that you're getting or the cutoffs that you're getting from the ionosphere is valuable to someone else. Is that data being utilized? Is there good science in that?
Somewhat. So actually one of the reasons we can't really use frequency below about 20-ish megahertz is because that's where people are doing ionosphere research specifically. They like that the ionosphere is starting to get opaque down there.
Right.
So that's good for actually understanding the structure. And I guess we are getting free data because we do see people's ionic signals that they're sending out. Yeah, that is RFI to us, but it's meaningful to them.
So can you pull tap out of your data, like total electron content of the ionosphere and isolate like localized ionospheric blobs? Do you know?
Yeah.
Or is that you need to get different frequencies for that?
No, I'm gonna answer that. I plugged in my laptop because I forgot to plug in my laptop. So, actually, I was showing those sources that are moving around in the visibility data, and I mentioned that they're moving around somewhat sinusoidally. That is actually evidence of a traveling ionospheric disturbance, and that's produced here on Earth. Unfortunately, that's not like super informative for learning stuff about, like, say, the sun or the sort of interplanetary medium. But it does give information about like the plasma moving over a mountain, which is really interesting. I'm not personally equipped to study, and there's no one currently in the group at OVRO-LWA, I think, for studying. If we had higher time resolution, we could do studies of the interplanetary simulation. Actually, I didn't talk about this data mode, but we do have what's called fast visibilities. I was showing slow visibilities. The fast visibilities use a tenth of the number of antennas, but operate 10 times faster. So good possible use for those studies. Cool. Yeah.
Thanks.
Another question. So, how well do we know the magnetic field information for the sway stand?
Great question. Well, Drama just had that paper put out, so now I'm figuring that out pretty decently. There's CDI and Zealand Doppler imaging of Drama. So it can actually map magnetic field topology. Epsilon Danny, I think we have a sense of this magnetic cycles. I don't think that we have a good impression of what its actual field topology is. I think that's the same for most of the stars. Actually, we have a sense of their magnetic cycles and their links, but not their topologies. Or their strengths are generally like a couple hundred Gauss.
That explains is that so the LWA band is set up in a way such that you would be sensitive to type 2 bursts from the sun. And that relies on the plasma environment of the sun and whether or not the sway sample at young age is dwarfs, where that plasma environment may be more dense, such that the bursts are maybe moving out of the band. As you dig into like the broader sample and the extended monitoring, do you feel like you're able to disentangle some of these issues?
I really hope so. So these fields are stronger, which means that moving out to a regime where you actually get a shock is going to be further out, hopefully where the plasma is lower density. So that could very well put a constraint on, say, like where the closed field regime is for these stars. That'd be super exciting, but I'm not, one step at a time, I think.
More questions? All right, thank you,